Alright, so I'm going to be talking about functional equations. So in functional equations problem, you are asked to find all functions f, and you are given some domain and range, for example, from the real numbers to the real numbers, that satisfy some equation. The first example I will give is going to be x plus y times f of x minus y equals f of x squared minus y squared. And this is a problem from Canadian Mathematical Olympiad Qualifying Repechage 2017. So how do we start with these problems? Well, a good first thing to always do is guess a function that will satisfy this equation. So just by looking at it, we see that f of x equals x is going to satisfy this equation. Since we have x plus y times x minus y equals x squared minus y squared, since this is a difference of squares. And we can also see that if we have f of x equals kx, this will also work because we get 1k on this side and 1k on this side, so we'll get x plus y times k, and we'll put the k out here, times x minus y equals k times x squared minus y squared. And this also works. And other than that, you can play around with it a little bit, but you may not find any other functions that satisfy this, so we conjecture that f of x equals kx are the only functions that satisfy this functional equation. And now the difficult part is proving this. So what we notice with the difference of squares here is very helpful. So we can rewrite our equation as x plus y times f of x minus y equals f of x minus y times x plus y. And now we really don't like x plus y and x minus y. There's lots of stuff going on and we sort of want to simplify our equation. So what we're going to notice is that for all a and b, there exist x and y such that x plus y equals a and x minus y equals b. And there's a couple ways to see this, that this is true. Algebraically, this is just a system of equations with two variables and two equations. And geometrically, you can see x as being the mean of a and b, so here. And then when you add y, you get a, and when you subtract y, then you'll get to b, since x is right in the middle. So now that we have this, we can replace x plus y with a and x minus y with b, and it will still be true for all real numbers. So I guess we can put in real numbers here. And this is going to also be in real numbers. Okay, so we replace x plus y with a times f of b equals f of ab. So again, this is for all ab in the real numbers. Now what we can do is simply plug in b equals 1. So let's set b to equal 1. So now we have a times f of 1 equals f of a. So let's just move over here. If we let f of 1 equals c, since f of 1 is of course a constant, then we have that f of a equals c times a, as desired. And we've already shown that all of these equations work. Thus, these are all the solutions to this functional equation. Cool. So that's a very simple functional equation. But we're going to try a little bit of a more difficult one where we may need to use some more advanced techniques. So our second functional equation is going to be f of x. Once again, we're going to find all functions f from real numbers to real numbers that satisfy this, plus f of y equals f of x squared plus y. Now, once again, we can guess what kind of function f is going to work. And once again, f of x equals x is going to work for this function. And you'll find this is a common theme with functional equations. So often the solutions are linear, or f of x equals to x. And we can see if we plug this in, we get x squared plus y equals x squared plus y, which is good. And you may also notice, after playing around with it a little bit, that f of minus x, or rather f of x equals minus x works. And once again, you can see that by plugging it into this equation, and you get f of negative x squared minus y equals negative x squared plus y, which just gives you x squared plus y equals x squared plus y. So it does satisfy the equation. After playing around with it more, you may notice that it doesn't seem that there are any other functions that satisfy this equation. And that's what we're going to set up to prove. But there's no trivial way to make progress like there was last time. So what we're going to do instead is just start plugging in values, random values of x and y, and see what happens. Often you want to try to get things to cancel out, so what we'll do first is we're going to set x equal to 0 and see what happens to our equation. So we get f of, this is just 0, f of y is equal to f of 0 squared plus y. Now this immediately doesn't seem very helpful, but we can use a little bit of another trick here and set y to be equal to negative f0 squared. And we do this because we want these to cancel on the right side and just to get 0. And you'll see why in a minute that is useful. So we get f of negative f0 squared, so this side is quite complicated, but it's okay. And that's going to equal to 0 because this and this are going to cancel out. So, once again, it may not look very helpful, but if we denote this inside part is just some constant u, then we found some u such that f of u equals 0. And this is very helpful, because now if we plug in x equals u, we will see that we get f of y equals y. And this means f is an involution. And knowing that f is an involution is very overpowered in functional equations problems because it implies that f is bijective. And we will prove that. But first, let's talk about what bijectivity is. So, a function is bijective if and only if it is injective and it is surjective. So first of all, injective means that f of a equals f of b if and only if a equals b. And surjective means for all b in the range of f, there exists a in the domain of f such that f of a equals b. And now we will prove that these are both true for the involution function, which is, or any involution function, which is satisfies f of y equals y. But if you come across this on a contest, you can just state that since it's an involution, it is bijective, since this is extremely well known. But of course, we'll prove it here. So first, for surjectivity, we first note that f of b equals b, since it's an involution. And then if we just set a equal to f of b, we get our desired result, which is that f of a equals to b. So we've proven that it is surjective. Now to prove that it's injective, well, first of all, one of the ways is trivial. A equals b implies f of a equals f of b is true for all functions. Each input must only give one value for it to be a function in the first place. So this is trivial. And the other case is that f of a equals f of b implies a equals b. And this is also very trivial when it's an involution, because we can just apply f to both sides using this first direction that we proved before, or that is trivially true for a function. We have f of a equals f of b, and since it's an involution, f of a is a, and f of b is b. So we get a equals b as desired. Thus, all involution functions are bijective. So now that we have that this function is bijective and it's an involution, we can continue with our problem. We'll go on to a new page here, and we'll go back to the original problem statement, which is that f of x times f of x plus f of y equals f of x squared plus y. Okay, now where do we want to proceed with this? Well, we don't like these f of x's, and there's a nice way to get rid of them when we have an involution. So since it is surjective, we know that there exists z such that f of z is equal to x. So let's set x to f of z and see what that gives us. So x is f of z. Then we have f of x, which is going to be f of z. You'll see why this is helpful, because this f of z, because of the involution, means that it is actually just z plus f of y, but for the sake of completeness, we will write it as f of z for now, equals to f of z squared plus y. Cool. So now if we replace f of z with z, we get f of z plus f of y equals z squared plus y. But you may notice something very interesting here, is that this side of the equation is the same as what we started with, except we just renamed x to z. So that means we can replace it with this side of the equation. Specifically, we can replace it with f of z squared plus y equals z squared plus y. And now our y's cancel out, and we get f of z squared equals z squared. Taking the square root of both sides, we get f of z equals plus or minus z. So now you may think we're done, because we did show that both plus z and f of z equals z and f of z equals minus z worked before. We know that this is a valid function, and this is also a valid function. Let's put for all z here. Of course, in the real numbers, the domain. However, this is just true for every z. So some function, for example, f of z equals absolute value of z would also satisfy this, since it is always either positive z or negative z, but it changes. So what we now need to do is prove that it is either always z or always negative z. So what we'll do is we'll strive for a contradiction. So let's assume, for the sake of contradiction, that f of a equals a for some a, and f of b equals negative b for some b. So it changes at some point. And then let's plug this into our equation. For example, this equation here. So if we plug a and b into here, we get, for example, f of a plus f of b equals a squared plus b. Now, replace f of a with a, so we get f of a squared minus b equals a squared plus b. Now we have two cases. For this value, or for this input, a squared minus b, we either have f of, let's let it be u, we either have f of u equals u, or f of u equals negative u. So if it equals u, then we have a squared minus b equals a squared plus b. These a squareds cancel, and we get b equals 0. And that's good, because of course f of b equals negative b is going to be satisfied when b equals 0. And then if we assume that f of u equals negative u, we get b minus a squared equals a squared plus b. B's cancel out, and we get a equals 0. And once again, this is good because if f of x equals negative x in the general case, then f of 0 still equals 0. So we've shown that if two are different, one of them must be 0, so they aren't actually different. And thus, the only solutions to our functional equation are going to be f of x equals x, and f of x equals negative x. And we are done. So there's no formulaic way to solve a functional equation. A lot of it is plugging different variables in and trying to get different things to cancel out. And then there are little tricks like the involution trick and injectivity, surjectivity, bijectivity. But other than that, it's just a lot of practicing different kinds of problems, and we will have a problem set that you can practice on, as well as different video solutions for each problem. Cool.